Good morning, good afternoon, or good evening, depending upon what time you're watching this video. This video lecture is made for the course ENSC112 or heat transfer. If you think about it, this course is taken usually after you have already backgrounds in thermodynamics and fluid mechanics. It's just simply because that we'll be needing or will be using concepts from thermodynamics and fluid mechanics in solving some heat transfer problems. Although heat transfer is actually independent, it's an independent subject and it concerns itself differently from the concerns of thermodynamics. What I mean by that is, if you recall that in thermodynamics, there's this first law. Say we have either closed system or open systems, and we have energy interactions and interactions in the term in the form of heat or work. So because of those interactions that's entering or leaving the system, then there's actually going to be changes. There's going to be changes in the energy of the system itself. Okay, so for example, we have this system. Let's say we have a cup of water initially at, let's say, 27 degrees C. So that's the initial state, the temperature, initial temperature. So if heat is added into the system, into that cup of water, then the temperature of the system will will actually rise. And let's say it's draw it here. So let's say here is our system, a cup of water, and then initially our temperature is, let's say, 27 degrees C, and then we add heat. So if we add heat, then there's going to be a change in the temperature of the system. So let's say the final temperature becomes 90 degrees C or something, right? So of course there's going to be changes in the volume if it's open, right? But the point here is that thermodynamics doesn't concern itself how does heat enter the how does heat enter the system. Is it by conduction, is it by convection, or radiation? All it concerns is it senses only the value of heat and heat in general, but it doesn't concern itself with how does heat enter the system. And that's the distinction between thermodynamics and heat transfer, because heat transfer deals more with how does heat enter the systems. Okay, so it's actually an independent subject. We can say that it's independent and it's totally different, but of course you'll be needing the concepts from thermodynamics and fluid mechanics in solving some heat transfer problems. Okay, now let's start with this word heat transfer. So now let's define what is heat and what is transfer. So heat, actually there's a lot of description about heat, and one description is that heat is an energy transfer process due to temperature difference. Okay, so whenever there's a temperature difference between 2 points, so whether it's 2 points in the wall of structure, or whatever, 2 points, any temperature difference, there's going to be transformation of energy due to temperature difference, and that is heat. Whereas another description is that they say that heat is an energy. The energy itself, this one is the transfer process, not the energy. Okay. However, if you recall that in thermodynamics, heat has a unit of energy. It's, let's say, kilojoules or British thermal units, right? But in concept, I think this is more precise, it is just a transfer process due to temperature difference, and it's not the energy itself. However, by convention, we use the unit of energy in describing or in quantifying the value of heat. Okay, so let me illustrate that. Let's say you want to withdraw money from the bank. So you can either withdraw from, let's say, from ATM machines, or from the ATM. ATM machine using cards, ATM machines, or you can either withdraw using, let's say, checks, or how do you spell that? I don't know, checks, or maybe this. Okay, inside the bank. So you can go inside and then have some queue before you can withdraw the money that you want to withdraw, or you can just withdraw through ATM. So here are just some of the process. So you can either withdraw through ATM, or you can withdraw through the teller or inside the bank. Okay, so that's the difference. So the process itself is not the money, right? It just processes the money. So that's one way that's described using this concept of describing heat as an energy transfer process rather than the energy itself. And what is transfer? Transfer is actually a movement or a change of, we can say, a change of location, or movement. We can just write movement or motion. Okay, and sometimes this is a misnomer, because heat is already a process. It's already a transfer process, and yet we still say transfer, right? A transfer, but by convention it's just called heat transfer. So let's just deal with it. Let's just accept that for now. And in detail, the subject of heat transfer is actually to have a detailed discussions, or to establish the principles and the equations about this transfer process. So the transfer can be either by conduction. Okay, so that's number one process. Number two is convection, and number three is by radiation. So these three, they are actually the basic modes of heat transfer. And the subject of heat transfer, again, is just actually to have a detailed discussions, also deal with mathematical equations regarding the conduction, convection, and radiation. So simple as it seems, and it can also be expressed in simple terms actually. In this first week of our lecture in heat transfer, we'll just deal with basic equations regarding conduction, convection, and radiation. So before we move on, this is our contents for this video lecture. We'll first discuss, actually we have already had a brief introduction between the difference between the heat transfer and thermodynamics, and also temperature difference. We need to emphasize this because heat, the prerequisite of heat is actually a temperature difference. Although there are cases wherein, if you think about it, like for example, the phase change of water. So if you recall in the course in thermodynamics, let's say we have this TS diagram of water, and we have this graph right here. So this curve right here, this is what we call the saturation curve, and this line right here, this line this is the constant pressure line. Constant pressure line. Okay, so let's zoom this in. So what you'll see actually is this, right? So right here, this is, let's say this is the freezing point of water, and this one is the boiling point of water. Freezing, and this one is boiling. Okay, so at 100, I think 101 kPa, the boiling point of water is 100 degrees C, and the freezing point is 0 degrees C. So this actually changes depending upon the atmospheric, or not atmospheric pressure, depending upon this pressure line. So if it's not 101 kPa, then of course you're going to have a different value for the boiling and the freezing point. Now, for discussion purposes, let's just say this is 101 kPa. This is atmospheric pressure at sea level. So our freezing point is 0 degrees C, and our boiling point is 100 degrees C. And let's say this is 0, right, from this zoom in portion, and this is 100 degrees C. So initially, let's say here's our initial temperature for the water, which is 27 degrees C, and then we heat it up. So if we heat it up, then it will increase its temperature, right? So let's say here's our 90 degrees C. So you see there's a change in temperature. However, right here in the phase change, the temperature is actually constant, but the phase is changing. Okay, so that's just one concept we're in. I just think that maybe heat transfer is not just limited to temperature difference. I'm not just sure yet, but this is one way. Okay, so to change phase from saturated liquid to saturated vapor or steam, right here, to superheated steam, then of course there's going to be additional of energy, and let's say the energy is heat. So how does heat enter the system? That's still going to be a concern of I think heat transfer. Okay, it's just that it's not described in terms of temperature difference, but rather in terms of phase change. Okay, so what else? Okay, temperature difference, and then we'll also discuss just a brief discussion about the law of conservation of energy, and then some nomenclature and some conversion factors, and also the three modes of heat transfer. So conduction, convection, radiation, and we'll have some computations, basic computations regarding each of this type of heat transfer. Okay, so here is our lecture handouts, and we have here heat transfer versus thermodynamics, and I have already explained that the thermodynamics concerns itself with the initial and final states of the systems, and it just sends the magnitude of let's say heat. However, it doesn't know whether how heat entered the system. Is it through conduction, convection, or radiation? Whereas heat transfer, that's the concern. I mean, how does heat enter the system? Okay, and also heat transfer is a dynamic phenomenon, which means it is a non-equilibrium in nature, and therefore the principles in heat transfer cannot be based entirely on thermodynamics, but also on correlations from conducting experiments. So let's say correlations, these are equations that's coming from an experiment or research. Okay, that these are empirical equations wherein you cannot just derive it from the basic fundamental equations. Okay, and then again, I just want to emphasize this temperature difference. So why do I still emphasize temperature difference, even though I also showed you about the phase change? It's just simply because much of the actually the equations, the conduction, convection, and radiation equations, they all deal with temperature difference. That's the delta T. Okay, and just take note that heat is transferred from regions of higher temperature. So we have T high to T low. Okay, so here's um, our direction of heat flow. So from higher temperature to lower temperature. Okay, that's of course natural process. But if we want to include work, then we can actually, refer to the to principles from refrigerations. Okay, and right here, the heat transfer and the law of conservation of energy. As I've said, although heat transfer is an independent subject, we'll be using sometimes the the concept from the thermodynamics to solve some heat transfer problems. Okay, and some nomenclatures and conversion factors. So since we'll be dealing with heat, so let's discuss this. Heat, we have, there's actually a lot of quantities that look similar. Okay, take note again, they just look similar, but they're not actually, they're not really that similar exactly. I mean, okay, like this heat, we have a term heat, and we have another term heat flux, and we have a term heat rate, and we also have a term heat generation. So when I say heat, we use the symbol Q without any extra marks. So the unit of this heat is the unit of energy, kilojoules in SI units, or IP. This is inch pound units, or English units. That's the British thermal units. The conversion is this one. Now heat flux, this is heat flux, that's the heat, actually that's the heat rate per unit area. So if you check these units, this is watts per meter squared. So how do you get watts from kJ? This is 1 kilojoules per second. That's equal to watts, right? So that's the heat rate, because that's rate, that's per unit time, and except that this is still per unit area. Okay, so what that means is, for example, I have this wall right here in 3 dimension. I have this wall, and there is a heat flow from this direction to that direction, right? So sometimes if the area is not given, or sometimes what is just wanted is the heat flux. That's the heat rate per unit area. So something like a unit area, let's say 1 meter by 1 meter, or any other units, any other uh, any other dimensions, right? So that's just heat rate per unit area. Okay, and the units is per area, and here's the equivalent for the IP units. That's the BTU per hour per feet squared. Okay, again, BTU per hour, because BTU itself is just energy, so this is BTU per hour. And then the heat rate, this is watts, right? This is watts alone, or BTU per hour. And we have temperature as well. So temperatures, there's actually a lot of quantities regarding temperatures. Is it the temperature of the surface, or is it the temperature of the surroundings, or is it the temperature of the fluid? So we have the symbols right here, and the units is in Kelvin, or degrees Celsius, or Rankine, or degrees Fahrenheit. Okay, so now let's move on to the 3 basic modes of heat transfer. So as I've said, we have conduction, convection, and radiation. So conduction, convection, and radiation. Right. So conduction is actually heat transfer within the medium. Right. When I say within the medium, let's say here's our medium. Let's say here's a solid medium, and the conduction of heat is within that medium. Okay, so I mentioned about solids, right? But technically, we can just, the technical definition for that is within the medium. So medium can be either solids, or liquids, or gases, except that the I mean, most problems encountered regarding conductions are solids. It's just simply because liquids and fluids, when they are heated up, they actually move already. So unlike for solids, when heat passed through the medium, it's not actually moving. So again, conduction is a transfer of heat within the medium, and usually that's solids. Okay, another one is convection. So convection is usually the transfer of heat between a surface, okay, a surface that's a solid surface, and the fluid motion. So when you say fluid motion, that's fluid motion that can be liquid or gases, let's say air or water or whatever fluids, right? So because of this heat surface, let's say we have let's say this surface has a higher temperature than the air that's flowing. So as we have defined that that heat travels from region of higher temperature to lower temperature, so the heat flow would be going from the surface to the fluid, actually, to this. Okay, so in this conduction, going back, before I forget, this direction is just simply because, I mean, if this is the direction of heat, then that means that this surface, let's say TA, and this is T sub B. So we can see that TA is greater than T sub B, right? So that's going to be the direction of heat. And for convection, going back to convection, this is just simply the heat transfer from a surface to a moving fluid. Okay, so there can be maybe fans or by natural convection. Later on, we'll discuss that in detail. And this one, radiation, is another heat transfer process. Just simply because any object or any body that has a temperature above 0 Kelvin, it's actually emitting and absorbing radiation. Okay, so again, radiation is just simply because a body is above 0 Kelvin, then it actually emits radiation and it also absorbs radiation. Okay, so meaning that radiation is a heat transfer process wherein even though there's no medium that's going on, it can transfer. Like for example, another surface is right here, right? So this surface is emitting radiation or emitting heat to this surface, and also it is also absorbing radiation, okay, even without a medium. Alright, so let's take a look at this example in figure 1-2, that heat transfer in an internal combustion engine. Okay, so here in our example, we have an internal combustion engine that is air cooled. So that's one type of one classification of engine, because engine operates, when it operates, it actually generates heat inside here, the cylinder, and that heat it has to be actually, there's going to be a maintaining temperature. So we can't just let the temperature here in the wall gets to infinity. So somehow we need some means to cool this engine. So one way is through air, and another way is by using water, and that's why maybe you heard about water cooled engines or air cooled engines. This one is typical in motorcycle engines, wherein you can see some fins that's protruding outside. So that's just simply to increase the surface area, so that when air passes through the surfaces, then it actually it can pick up some heat. Okay, so right here's our situation, and you can see that if we zoom this in, what we see is we have conduction along the walls of the combustion chamber. Okay, so we have conductions, and from this wall to the surface, because of the motion of air from the outside, then there's going to be convection. Okay, and radiation exists is just simply because the temperature of the body is greater than or is above 0 Kelvin, so it has to radiate somehow. Okay, so we can see right here in this phenomenon that we can see the three basic modes of heat transfer. All right, so now let's move on to let's have a detailed discussion about conduction. So for conduction, it's actually proposed or originally came from Joseph Fourier in 1822, and that's why sometimes it's referred as the Fourier law of heat conduction. Okay, so the equation is this. So we have this heat flux, right? Heat flux is equal to negative K times the gradient delta T all over delta X. Okay, so K is the K is what we call the thermal conductivity of the material. So different materials will have different values for the thermal conductivities. And where can you find this? You'll be able to find this in tables. And sometimes it's expressed as a constant value. So here in table 1-2 we have some selected, thermal conductivities of selected materials. So this is in watts per meter Kelvin. Okay, take note. Or in IP units we have BTU per hour per foot Fahrenheit. Okay, so what this says is that heat is just simply directly proportional to the temperature gradient. Okay, so take note, when I say temperature gradient, I refer to delta T divided by delta X. But for delta T, this is just the temperature difference, right? Temperature difference, and the delta X is the let's say is the thickness. Okay, so here is the heat flow. So right here we have, let's say, a plain wall, and here is our area. Okay, here's our area, and here's our thickness. So you'll notice that the area is perpendicular to the heat flow, to the flow of heat, and the thickness is the dimension, or is the length dimension that is parallel to the heat flow. Okay, so delta X, sometimes in some literatures they use L rather than delta X. So if we detail a section, we'll see this. So we have this heat flow from this region to that region. That means that this the temperature at this surface is higher than the temperature at this surface. So that's why that's the direction of heat flow. And here's our delta X. And the graph right here, sometimes you'll see some lines. It's actually a graph between temperature and the distance X. Okay, so again, heat conduction equation is actually just says that the heat flow, and if you recall, conduction is a transfer of heat through a medium, and usually it's a solid. So it's what it says is that that heat is or the heat flux or the heat rate is directly proportional to the temperature gradient. So here's our temperature gradient. That's the slope of this curve. Now if you take a look at this, by the way, that's heat flux, but if we talk about heat rate, then we have if we talk about heat rate, then Q dot is equal to K, negative Ka delta T all over delta X. By the way, this negative sign right here is just simply because that heat travels from regions of higher temperature to lower temperature. So you see here T sub 2 is lower than T sub 1. That's the reason why there's a negative. Okay, and also if we check the thermal conductivities of material, we have here carbon steel, aluminum, what else, plastics, bricks, water and air, and also some woods where I forgot to input some value here. But as you can see here, carbon steel, that's the typical mild steel that we can see in fabrications, in constructions. Carbon steel, so it's just 43. We're in aluminum, 237. So that means that it can pass this much. I mean, we can say aluminum can transfer heat faster or higher than the carbon steel. And I've also included here the value for water and air. So you can see here this is 0.6, this is 0.026. We're in aluminum, this is 237. So that's the reason why actually when you cook rice in an aluminum cooker, or I mean rice cooker, it's actually much faster if you cook rice in let's say using stainless steel. Okay, so I guess I don't have much time now, and we'll continue our discussion in the next video.